All right. Good morning, good afternoon, or even good evening, depending on where in the world you are. My name is Michael Carducci, and I am a hands-on software architect by day, but I live in this intersection between magic and technology. Whatever that intersection is, I don't know. Maybe something like a digital alchemist. I have no idea at all, and we will figure that out. But I am really excited to dive into the topic today. So we're joined in the studio by Brent Laster, and we're going to be talking about containers. And as you know, we've been discussing this. Containers are all the rage these days. Everything from Docker to Kubernetes and everything in between. And the question that we're going to be diving into is how do we get the most out of them? And in order to do that, it can be helpful to understand some of the lower level details, how they're constructed, how they depend, and how they interact with the operating system, between different layers, with the images, storage drivers, all of these things together. So we've got Brent Laster in the studio. He's a speaker, author, and research and development director. And we're going to get a little bit of a visual overview of how the containers work and how all these applications work with them. Brent, how are you?
Doing well, Michael. Thanks for the intro.
And
All right.
I want you to go ahead and go ahead and dive right in, because I know you've got a lot of content for us, and you've even got a bit of a presentation. So I think a good place to start would be right there. And folks, if you've got questions, if you want to dive in deeper in any particular aspect as we're going through this, go ahead and drop everything into the chat, and I'll be moderating, and we will dive from there. But for now, I'm going to mute, and everything is over to you, Brent.
Great, Michael. You can see the slides there.
I swear that is the mantra of 2020. Can
I
everybody
know.
see my screen? But yes, and it looks
I
great.
saw something the other day. It's something like, God grant me the confidence of the person who asks or who puts the slideshow up and doesn't ask if you can see my slides. So I'm not that person though. So glad you guys can see them. So welcome everyone, and I'll say it again: good afternoon, good morning, good evening, depending on where you're joining us from. And thanks for taking part of your day or night to spend here and join in this webinar from the No Fluff Just Stuff group here. As Michael said, my name is Brent Laster. We're going to talk today about the backstory in containers. I called it kind of the subtitle, Understanding How Containers Work to Work Better with Containers. And a little bit about me. We don't want to spend too much time on this, but Michael's already mentioned my day job as an R&D Director. For fun, I do training and on various platforms and stuff, and you can find some things out on, I've written on opensource.com. There's a Git book, a Jenkins book, other things. If you want to connect with me on social media, feel free. There's some connection information. A couple of books I got out of there, Professional Git. If you're interested in learning more about Git from either a beginner or a advanced topics, feel free to check that out. Jenkins 2 book. If you know Jenkins or want to know more about Jenkins and pipelines as code in particular, check this one out. If you do happen to get this one, I'd suggest the electronic version, because it's the printed version has some kind of washed out screenshots there, but still think it's a decent book. And our agenda today, we're going to talk about what containers are and the benefits they provide. And chances are you may already know some of this, but I never want to assume for an audience that's learning about containers that they know all the ins and outs. So we'll do kind of a quick overview of those. And then we'll talk about how containers are constructed, and particularly the differences between layers and images and how those get built into containers. We'll look at what does immutability really mean, this idea that you can't change things, that things are put together and you aren't able to make changes in there. And we'll differentiate that between the images that make up containers and containers themselves. We'll also talk about the core Linux functionalities containers are based on. How does this really play in the operating system, and what kind of technology does it use in there? It's actually interesting that the container technology that we're using today is based on the Linux container technology that's been around for years and years and years. They've just a lot more formalized, a lot more easy to use today. We'll talk about how containers reuse code, and we'll get into some fun with storage drivers. You say fun? Well, it's interesting to be able to understand more how they work. And one of the things I really like to do in these kinds of presentations is what I call kind of removing the mystery of how things happen. Everybody knows what containers, or most people know what containers are and how popular they are. As we said, they're all the rage these days, but how do they really work? And once you understand a little bit about what the operating system is doing and the storage drivers in there, it takes a lot of the mystery out and also helps you understand what you can really kind of do at that level and what you can't do, and why some storage drivers might be better than the others. We'll look in particular at the overlay 2 storage driver. That's the current hot one right now and the default one that's out there, and talk just briefly at the end about the Open Container Initiative. So let's go ahead and jump in. So what are containers? Again, I'll kind of just quickly go over this. Standard unit of software functions like a fully provisioned machine, or a way of packaging up software. It's basically a way in an operating system to carve out these resources and give an application running in there its impression that it's running in its own machine, it's running in its own system. Anytime you see and hear talk about containers, you're going to see the obligatory picture of the container cargo ship, with the idea of carrying on it all of the containers out there that have things inside of them. If we were to think about what was actually in a container from the software standpoint, you might think about one of these cargo containers having things like the application in it, the runtime, these dependencies, the settings, the system libraries, the system tools, all of the things that we need to have that self-contained environment for that application to run in. As far as the application is concerned, it's got its own machine it's running in. It doesn't know that it's existing with a lot of other applications on the same machine. But we have what's a container there, and when we talk about the container, it's important to differentiate it from a VM, VM being a virtual machine. A virtual machine, some of you have probably used things like VirtualBox as an application, called a hypervisor in that context, a way to actually host or run a virtual machine on top of the application. So VirtualBox, I use a lot of VMs in my own other classes, and a container leverages, instead of using that hypervisor to provide that layer to run on top of and having to have its own guest operating system, a container is leveraging several features of the Linux OS to carve out this kind of self-contained space to run in. Containers are built from images. We're going to talk about what the difference is between an image and a container. It's a slight but distinct difference there. And images define what goes into a container, and they're built from images. So if we talk about the benefits of a container, containers, because they are self-contained in there, they are easy to create and deploy once the image is defined. If you think about it from the standpoint of like provisioning software, you've installed software on a machine, on a disk in there. That software is installed there, is configured, it's ready when you turn the computer on, and it's ready to go. So once you've got it created and once you're ready, you want to use it, all you really have to do is turn the machine on or sign on and you're able to do it. Same kind of idea with container. Once it is provisioned, once it is set up and configured, ready to go, you can just deploy it and create it and start using it. So it allows us to do lots of things, lots of words on the slide, but essentially allows us to have that kind of a set provision of software there. We can kill it off and bring it back up immediately. We have the same software, the same settings, the same, all those things we saw in the last slide that go into it. We get observability through health and signals, and because it's self-contained, it can all run on this same infrastructure. It can run on anything that runs Docker, for example, or that runs one of the Open Container Initiative we'll talk about towards the end. One of the compliant applications for that can also host and run these kind of containers. But it's portable across any or OS or cloud that runs there, and you get to focus on managing the application. If I already have my environment configuration and all that set up, and I can just spin it up anytime I want, I don't have to worry about trying to provision it and trying to get everything set up and installed. I can take that image, create a container from it, and immediately start working on and focusing on the application that I'm trying to develop there. So it allows a lot of isolation and loosely coupled strategies there using the containers. But containers themselves are based on an image. And an image is kind of like a read-only template used to create a container. Container images are essentially like a snapshot of a container. What I tell people is think about if you've ever installed software on someone's laptop or desktop, perhaps for a relative. If you're like me, you may be tech support for lots of relatives around your home, or you may be do it at work. You may need to provision machines. So you install and layer all that software on, and then once you've got it on there, that's an image. That's an image that you could then take to another machine, put the same image on, and get the same software going. So you have that image, that sort of configuration provision software out there. Images themselves are stored in a registry, which is like a repository for images. And images are generally considered to be immutable. Immutable means that we don't change the image. We aren't allowed to change something about that image. We're going to talk about how that works in just a moment. The idea that an image is immutable, but a container is not immutable. So a distinct difference there. And sometimes people say containers are immutable. No, containers you can change, you can add stuff, you can create content in there. But images themselves are immutable. And the idea would be that if we need to change something in an image, we create another image. We create another instance of that image to work off of. And we'll talk about why that is and how that all ties together with the layers and things in a few minutes. But immutability, again, doesn't imply that containers can't be changed by configuration or environment, et cetera, because it's not the containers that are immutable, it's the images. Container images are built up from these things called layers. And we use the command, if we're running Docker, for example, build to create the images. So what is an image layer? Well, a Docker image is built up from a series of layers, and each layer is simply the results of running a step from this file we call a Dockerfile in the case of Docker. The Dockerfile is like a recipe or a script. If you were sitting down and installing a machine, a software on a new computer, laptop, desktop that you had, you might have a checklist to go through. And you might say, start off installing the base operating system, then install the antivirus, then install Office apps or something like that. You can kind of think of a Docker file in the same way. There's an example of one on the slide here on the right-hand side, and you can see it has keywords in it like from, copy, run, command. And you can probably build up an idea of what those mean. From, it means take another image, a base image, in this case, an Ubuntu Linux image, install it there, put it as the first layer, and then we can copy in some stuff locally from a location we have, do a run command maybe to make some other things. We could do configuration, all those kinds of things. But as we are going through and as we execute each of these commands in the Docker file, it in turn builds up an image in the image down that we are going to base our containers on. Not every command is going to actually create an image out there. Some commands don't always create images. It used to be everyone did, but they've made it a little bit more efficient there. But layers are only the set of differences from the last one. In other words, when I execute that step in the Docker file, it makes some change. It adds some content. It brings down some image. It configures something. That set of changes is in what ends up being that layer. And those layers get stacked together to make up the image. Each layer is read-only in there, except for the last one. The last was talking about container. And really, when we talk about making a container from an image, the image gets created from the Docker file, from the set of instructions in there. We talk about making a container from an image. All a container is really just putting a thin read-write layer on top of the image or pointing to that image. So if we have the layers of software that we have installed, provisioned, configured out there, and then we put this read-write layer on it, that read-write layer is what makes it into a container. So all changes made to that container are going to go into that top level layer. So if we were going to actually do a Docker build command here, and I'll show you an example of what we're doing here, what this command is doing is it's actually going and reading the Docker file that's shown in the white box on the left. And the first thing it's doing here is it's going to go and says from MySQL 5.5.4.5. The MySQL there is the 5 is a pre-configured image that someone else has created at some point in time that has MySQL embedded in it. It has a basic operating system, and then they install the MySQL app on it. And so now that itself, what image was made up of layers. And so now we're pulling down all of the layers that are associated with that base image. And once we get those down to our local disk there, then we'll go through, we'll add and we'll copy in some stuff from locally. We have locally on the disk, the copy. And then we'll set an entry point where to start out when the container starts up. And finally, we'll make sure that we have the MySQL daemon running. So you can see that building an image is simply a matter of going through and executing the steps defined in the Dockerfile. Now, if we were to go ahead and map this a little bit more closely to this, if we looked at that set of steps where we brought things down and we looked at the history of it, we could see the history of the image. And if you look at that bottom screenshot on the slide here, Docker history, it's showing us all the things that went into the image that we built. Now you'll notice here that there is a set of things here at the bottom that are, say, missing by them. So you can think of each line in the history as representing one of those layers. But the thing with the layers at the bottom that are marked missing in the history simply means the layers were built on a different system. So we're utilizing a base image of that MySQL base that somebody else created, and we don't have all of the layers there from that previous base image. We have that base image itself. So we pull that base image down. If we were to map this through, we might say that from the construction in the Dockerfile to pull down the MySQL image was executed by the Docker build, which created a layer in our image, which mapped to the set of layers originally went into that image. The next one was a copy, which again created another layer out there, shown in the history, and so forth. And you can see how all this goes together to create these different layers. So these colored layers that we have at the bottom here actually are what make up our image. And those things together then, each one of them is from one of those commands we executed in the Dockerfile. They are immutable. That means they can't be changed. So then it becomes a question of how do layers and images intersect with the operating system? So if we think of layers kind of like directories or files to the OS, they're immutable. They can read only. If we want to create a container, then when we do a Docker run command or command to create a container, it simply adds a layer on to the top of it, a read-write layer where changes can be made, mutable. Now it's hard to see probably in the screenshot, but it says Docker run and has a command there. So when we do the Docker run, it has that thin read-write layer on top of the layers, and we have a container. So the question becomes then, how do we manage files and stuff? If we can't change things within the layers of the image, how do we actually regularly use this? Are we able to work with this on a regular basis here to make changes and stuff? Well, as we mentioned, as I said, really Docker only is utilizing some of the underlying technology that's been around for a long time in Linux containers. And the main one that most of the drivers will use is the union file system, or a type of union file system. And the union file system allows you to essentially stack layers together and be able to drill through them to find things. A lot of times I'll tell people to equate this, think about the path variable. If you look at the path on any of your systems, Linux, Windows, whatever, you know the way that works. The path variable has a set of directories, and you start at one place, look through it, and if you can't find something, you look through to the next one, you look through to the next one, and so on. But it has a set of things chained together to be able to look through it. Well, the union file system functionality in there, if I have files in these different layers, the different color little boxes there, the union file system allows me to start at that top layer, that container layer, and look through to find the file that I need, to find what I need. So think of it as stacking those layers together on top of each other and being able to look through them, kind of like you search the path to find something, to find what you're interested in. Now, one of the questions that comes up though is, well, what happens if I need to modify one of these files? What happens if I want to change one of these files? You said it's read-only, it's immutable, and I can find them there. Well, it turns out there's another piece of functionality called copy on write, or CAL for short, which works by when I need to actually change one of these files, then I can actually just copy it at that point in time up to that topmost layer. Remember, that topmost layer is a read-write layer where we can actually change content, write content, update content. So all I have to do is get a copy of that file, copy it up to the topmost layer where I can write it. And because we have that sort of drill down looking through, that topmost copy that we can modify and change will obscure or hide the one further down in the layers. So you can see how we can use that copy on write functionality when we need to make a change to copy things up to that top layer. And then we have a change in the top layer, but our lower layers are still immutable. They have not changed. That's where we talk about with immutability. There's some other Linux functionalities like cgroups and namespaces to help us to keep the containers separate. But one of the other aspects of this is that if we create a container, as we said, it's a top level read-write layer. Because we have that layer and that all this content change is done in there, multiple containers can share the same underlying image. That means once I have the layers down on my disk and I can build the images from them, I can create a lot of containers based on that image, but I don't have to have additional copies of the layers. I can have one copy of the layers because they are read-only, they are immutable, and then I can have multiple container layers as shown in the diagram here, pointing back to that same image. That means, for example, if I then do, it also simplifies some things so that only the layers that change need to be updated. Those layers themselves are stored on your disk by default in var live docker. And we're going to talk about in a few minutes how that looks on disk, how they're stored, and how they're accessed in there to give you that little bit of a deep dive into it and kind of remove the mystery around that. So Docker uses storage drivers to manage the contents of the image layers and the writable layers to hook them all together. But it also means that if I then, for example, on the right-hand side here, I've got this little example off from the Docker website. Docker pull Debian, it pulls down a couple of layers. And then if I pull down Debian Jessie, the layers are already there. So if layers are already there, stored in that var live Docker area, I don't have to get another copy of them. I don't have to use that disk space. I can simply have one copy and I can make as many containers as I want off of that simply by having more read-write layers that point to that. So Docker, we've already mentioned, is a platform for managing these containers. Technically, though, it is a thin wrapper around Linux container technology. These Unix files, Union file system, namespaces, C groups, we're going to talk about more what those are in just a moment. But Docker was really the first one who successfully provided this kind of thing, the REST interfaces, description format for containers, ways to build them together, the APIs, all those kinds of pieces. So we mentioned the Union file system that we can drill down through and find files. The other pieces that we have that are the main things that Docker leverages are C groups and namespaces. C groups is short for control groups. And this is groups means it groups processes for the purposes of managing system resources. It's a feature in the Linux kernel to track, isolate, limit resource usage. For example, we might think of system resources as being things like CPU, memory, I/O, and a network. And a C group, if you think of a group control group controlling a group or set of resources, you might have a portion of the CPU, a portion of the memory, a portion of I/O, and a portion of the network that's allocated for a C group. And that means that then that is allocated for a particular app running in the container to be able to leverage. Likewise, we have namespaces that provide isolated instances of global resources. We have different kinds of namespaces. We have a process ID namespace, allows processes in different containers to have the same PID. So again, this idea of isolating, being able to present or to represent a separate isolated resources out there. Each container has its own PID1 process to manage initialization task. Networking provides isolation of network controllers, system resources, networking, firewalls, routing tables. Mount, there is a namespace you can have for isolating the set of system mount points. Each container have its own temp or var directory. Interprocess communication, such as system v IPC objects, message queues, so on, shared memory. User namespace, range of host UIDs in there. UTS, use time sharing service, node name, domain name in there allows each container to have its own host name and NIS domain name. So all of these are resources within the operating system that the Docker technology leverages to be able to allow each container to have its own namespace, its own C group, its own area there, its own resources to work with. That's why I say it's like carving out sets of system resources to give to an application to work with. Dockerfile, we've mentioned, is just a set of instructions there to be able to pull in, do commands, and configure and provision software in it. Each instruction in a Dockerfile can create a read-only layer. Not all of them will, but it has a specific format and structure. So overall, the kind of workflow, if we're talking about using Docker, is we take the Dockerfile, we build an image out of it, then we run it. We use the Docker run command to add that read-write layer on top to have that container that we created then originally from the Docker file. Docker commands, Docker has a number of commands, and if you've ever used Docker, you're probably familiar with several of these, but the build takes an image from, or produces an image from a Docker file. Docker images lists out the images. Docker RMI removes the images. Pull brings down the image from a repository. Tag allows us to give that human readable name to it. Push allows us to push it up to the repository. Run turns it into a container. And then we have stop, kill, different ones to stop things, list things out, and so on. How do we think about this? Well, I've already alluded to it, but sometimes it's helpful, I think, to have an analogy to think about a way of containers and images. So if you think about, again, this idea of installing software, provisioning software on a computer or on a laptop, you might install the operating system first, and then, like I said, some Office apps, maybe an antivirus. So you are layering on the operating system first, then you're layering on productivity software, then maybe layering on security software, and ultimately you have produced an image being a provisioned, configured set of software that can be used to, in this case, provision other computers. If we were to take this then and provision a system, we might think of that as being like having an image, right? We have the image there. Then if we wanted to think of a corollary maybe to a container, we might think of actually creating like the user space or the user profile on the computer or on the system. Because if we think about it, when you create that user profile, you are setting up an area where the user can work, they can write files, they can change content. They're not typically going in and modifying the already provisioned system software. They're at that layer on top. So kind of like containers, we can create that layer for the user. Likewise, from the same image, we could create another system there. We could layer on the user space there. And so we might actually think of that provisioned disk image as being kind of like a image there for Docker, and the turning on the computers, having that read-write layer, the area for a user to work, as being kind of like a container. Again, just an analogy is give you a way to kind of think about it. And just like a disk image or a computer when it's turned off, that image is still there. The software is still installed, it's still configured in a Docker image. You just need to activate it, turn it into a container, and you can use it. All right. So we'll go ahead and jump into, unless there's some questions, and Michael, I'm assuming you can interrupt me if we see questions come in.
Yeah, nothing left, nothing yet. So that, if nothing else, that says to me that
I'm putting everybody to sleep, or
or you're explaining everything very well. The
all
fact
right. Well,
that folks are also, yeah, no, I think so far this makes very good sense to me. But just as a
great.
reminder to folks that if you do have any questions, if you want to get a little clarity on any point raised, feel free to drop something into the chat, and we'll go from there. And in
Fantastic.
fact, folks are saying we're getting consensus right now that very clear, good stuff, very
Awesome.
clear. So
All
so
right.
far,
Well,
at least all the Jims are in agreement.
Okay.
Because we've got Jim A, Jim T, and and Jeff W.
All the
I
J's.
need to upgrade my glasses here, but the J's are in agreement. But yes,
Fantastic. All right.
but we will get some questions here soon on some other operating system containers.
Okay. All right, well, let me dive deeper here and see if I can try to be as clear. Maybe a challenge of some of the stuff, but we'll see what we can do. So diving deeper into layers. So containers can reuse layers. We mentioned that containers are built on top of layers. And Docker commands can reuse layers. You may remember that picture. We had all the different layers at the top that were pointing down to the same image. This is just kind of another expression of that. You can see if we do a pull, we get an image, we get a layer down on our system. Then if we go to pull something else and it needs the same layer, it'll already be there, already exist. And you see these layers have the hexadecimal IDs and the thing called the SHA-256, the digest there. I'll talk about what that is in a moment. Prior to version 1.10 of Docker, when we talked about pulling a layer down and an image, the layer is essentially, well, this is not prior, but the layer is a delta or diff that results when commands are run during the build process that produces new or changed files directory. All that says is that when I execute that command in the Dockerfile and it creates a new file or it makes a new directory or it copies something in, that change is what's stored in an underlying directory that represents the layer there. So it's a delta or diff from what was there before. The newer change files are stored and committed as a new layer. Now, when we used to look at, for example, list out the layers in an image, if we were to get the information about it prior to Docker 1.10, and you were to go and look on the disk, there was a one-to-one mapping. They had the same name. The layers that showed up in the image information would map directly to files or to those directories that were stored in the Docker area in 1.10. So you could actually inspect it and you could see, okay, I've got FDF9 here out on my disk somewhere. There is a thing called FDF9, that directory, and I can go and map that. The challenges they had with that, though, was that there was security. For example, how to tell if the image is tampered with during the push or pull out there, and other tricks, other things with that. So they moved away from that to something called content addressable IDs. Sounds very fancy, but it's really not that complex or not that fancy. It's just the idea that layers, as they are stored in the var live Docker area, don't have any affiliation or notion of an image. You can't necessarily go straight one-to-one correspondence from what's shown in the image, the information in there, and find that out on the disk, which can be a little bit confusing. But the layers themselves are just collections of directories and files, and they're identified now when we talk about what's showing what's in the image by what we call this digest or an algorithm of the form algorithm hex value. So as with many things, if you've ever worked with Git or anything else, you know about the idea of the SHA secure hashing algorithm. If you've ever used MD5 checksums, those kinds of things, SHA has descended from that. It's a checksum, it's a hash. And so we compute a hex value from the layer's contents, and then that becomes, for example, the algorithm. Which type of checksum did we use? Is it a SHA, in this case, a SHA-256? And the SHA-256 then value is the algorithm, the type is put in front of that. And then the checksum or the hex value is after that. And so that becomes the digest of it. So it's computing the layer is computing the contents. It's a value derived from the contents of the layers on there. So if you do a Docker inspect, and inspect is a way to show you metadata about the Docker object, you'll see the layers and they're expressed in this sort of digest format, which is SHA-256, and then the checksum, the checksum value, providing the SHA-256 checksum on it. When we get that, then the Docker image, that's with the layers themselves. The overall Docker image has a number of pieces, has configuration object in it, which includes an ordered list of layer digests. It's basically a file that just keeps track of everything in there. And the image ID for the Docker image itself is a hash on that configuration object. So when we talk about identifying layers and the images and those IDs we see with those are typically based on the hash that we have or the checksum that we have. And then the contents themselves are stored in different directories under var live Docker. If we want to get information about where things are stored for Docker and other information like what storage driver, we'll talk about storage drivers more in a few minutes, you can do Docker info. Docker info is an overall information about the Docker application itself. So in this case, you can see it says storage driver overlay 2, and then Docker root dir var live Docker. Pretty straightforward. Now, if you look at Docker on the Mac, sometimes you wonder how that's done. Docker is not really compatible with Mac OS as it is. It typically uses HyperKit and some kind of virtual image, a virtual image being something that runs either like in the HyperKit or Hyper-V or VirtualBox, you can use that. And so if you were to go out and look at where Docker is on the map, you could trace down into the library area and find the virtual machine. And then inside the virtual machine, you'd see that Docker is at, the layers are stored at var live Docker. Likewise on the Mac, or I'm sorry, on the Windows systems, you have the approach of native Windows containers, but you also have the approach of Linux containers, which are run in a simple kind of Hyper-V based environment. I guess I said Hyper-V before for Mac shipped and HyperKit, but the Hyper-V environment there. And then the config and info about the virtual image to run is typically going to be stored out in C program data Docker desktop. So we have different approaches to work on these non-native Linux or non-Linux systems there. Windows support has gotten somewhat better now. I don't know that it's fully there yet, but it's gotten better. If we were to look out in this kind of root folder for var live Docker, if we wanted to dive down a little bit, you could see some things here, and you could probably see some typical names or have some name recognition here. You see a containers directory, an image directory, network, registry, overlay 2, the driver, volumes, disk volumes associated with it. So you can start to get a feel for how this stuff is laid out on the disk. Under this var live Docker, where this thing, the information is stored. But let's talk a little bit more about storage drivers, or what we call graph drivers, and I'll explain in a moment why they can also be called that. So a storage driver is something that a local instance of a Docker image or uses, Docker engine uses to tie all the layers together, to be able to access things, be able to work with images, containers, and so forth. So a Docker image engine has a cache of image layers. That is, when we do a Docker pull or when we do a Docker build or whatever, we create these layers, and these layers get stored in var live Docker. And you can think of that area of just being a large collection of layers. Layers can come from other images, they can come from things we construct, however, they're all stored out there, ready to be assembled in different ways into images or containers. But we need a driver to go and manage the layers for us at runtime, to put them into consolidated file system, to create the mount namespace, to be something that we can use and we can run a container on. And so this kind of weaving through the layers, tying them together there, creates what was called at one point called an image graph, the relationship between the layers, how the layers all go together to form an image container. And that's where we kind of get the name graph drivers, but more commonly called storage drivers. I'm not going to try to go into too much detail on this, but just to quickly mention that there is a set of storage drivers out there that have been around for a while. AUFS is a union file system based one. It's the oldest and the most mature, fastest to start up. It's never really been accepted by the mainstream. It tended to, actually, it was fast to start up for a long time. I think overlay 2 is better now, but it was never really accepted in the mainstream, but it was used on a lot of distributions of Debian and such. BTRFS and ZFS, I'll use those two together, those are file system based. So rather than having something that kind of sits on top of Linux and uses this union file system approach to string things together, they actually use snapshots. They actually use the built-in file system functionality. Those are both file systems, ZFS and BT or B-tree file system. Devicemapper actually gets down to sort of looking at the blocks of stuff on disk and trying to use that to keep track of layers in there. And then we get into the overlays. The overlays are the new kids or the newer ones on the block here. They are the ones that make use of the union file system, but do it in a better way than AUFS did. And we'll talk about how that works in just a moment. Finally, there's VFS, not really a file system. VFS does sort of a brute force approach. It's the only one that actually doesn't reuse layers. If it needs to have multiple containers using a layer, it'll just copy the layers over. So it's very inefficient in terms of that. But it does have some use for typically developing or testing with Docker, and it can run anywhere because it's just doing copies. So the storage drivers tech, there are three different kinds of storage drivers you'll encounter. Will be the union mount file system, which is like we talked about before, the union file system, to combine multiple things into one, kind of like that path variable we talked about. The snapshot, which is using the BTRFS, the B-tree file system, the ZFS, uses their native snapshotting. Snapshotting is just a point-in-time copy of stuff on the file system. So every so often we make a copy of the way a directory looks in there and we save it off. And they use those in the same way we kind of use layers. They use a copy of that. The layers are represented by snapshots instead of the way they are with the union file system. And the device mapper is just a weird one that basically gets down to mapping physical blocks together to form the layers. So very quickly, some pictures here. The AUFS is the oldest, most mature in there. The idea here is on the left-hand side, we have the Docker concepts. On the right-hand side, we'll have the driver concepts. AUFS uses what's called branches. At the container layer, you can see basically it's that mount point. It's the way of viewing that. So you can view the files regardless of where they come from and what, in AUFS term, what branches they come from. Now, the one thing about this is if you have a deleted file, you may wonder how that works. Well, a deleted file just gets a special, they call it a whiteout file. If it's a directory, they call it an opaque directory. It's basically a blocker. It's a special file on there. You can't see it normally if you were to look at it. You know, with the extended attributes, you could see it, but it's a whiteout file or a blocker file that gets put there to kind of represent we've deleted this file at the top in the user's area or in the top level container layer, so we shouldn't see it going down. The overlay model has a single overlay layer. So the overlay layer or overlay model has the container mount up here. The same idea. I look through the layers to see where the file is and where I find it. But in an overlay model, it only really uses three layers: the lower directory, the upper directory, and the merged layer. Now, the merged and UpperDir may be the same essentially, but it only has one lower directory. So what they did to make this work, you can imagine if you only have one lower directory, if you only had that as a one layer option, that's not very useful. So what they did in the overlay model was they actually did hard links. They actually linked in, if you know Linux links, they did hard links to that lower layer. So they had all these other directories that represented all the layers of the image and they linked it in there. The problem with that then became that if you know anything about, much about Linux, you start running out of system resources because there's this thing called an inode, which keeps track of items in the file system, and you can run out of those. And all of the layers they had linked in to make this work, then to that one thing, used up a bunch of inodes, and you would hit inode problems with overlay. Overlay 2, they made it better because they said, we're going to make it so it can natively support up to around 128 layers in that bottom part. We'll just make it so it automatically does that. So they get away from the inode problem. Then the over device mapper, that's the weird one I said. It kind of it uses the file block, gets down to the block level. So because it's dealing in terms of block, it can be very inefficient in how it's doing that. The file system model, they use the snapshots, those point-in-time copies to emulate the layers out there and save those off. All right, so for the last part of the webinar here, I thought we would dive just a little deeper into the overlay 2 storage driver, and I'll try to get through this, make sure we get some time for questions here.
Yeah, we've definitely got a few queued up. So,
okay, do we want to stop and try to do those, or do you want to go ahead and go ahead and do through this and see if we answer some of those along the way, or?
Well, there's at least one here that's germane to what you're talking about right now.
Okay.
And the question is, are there any, this is from Roman, are there any reasons to not use overlay 2 driver for all the containers?
I would say not at this point. Now, in the past, there were some Red Hat and certain ones did not support it, so they would even use things like Devicemapper in there. But now they support the Overlay 2 driver as well. So there are claims that it still has problems with inodes at some, at certain, you know, if you get enough into it. But really, it's the most recommended and probably most reliable and best one out there, as far as I know.
Oh, right on.
Okay.
And the rest of the questions, so we got a thank you from Roman, and the rest of the questions I want to get kind of right at the end of the Q&A because they cover a couple different topics.
Okay, all right, let me go through this part. This is a little bit deeper dive into the overlay system here. So overlay file system directories or overlay process here, it's a kernel addition or kernel part in there. And essentially, it has those three parts, or four parts, I guess you could say technically. The LowerDir, which is the read-only image layers. And if you were looking at this as expressed like in a Docker list, you could see multiple directories listed, much like a path again, separated by a colon from the topmost to the bottommost. I'll show you what that means, looks like in a moment. The upper directory is a read-write layer where changes are written, corresponds to that idea of a container layer. Merge directory is a merged view of all the layers, being able to look through it. And working directory is just kind of something that's used by the underlying Linux overlay file system to work in. Now, just to make this a little bit less mysterious, you could actually go out to a standard Linux system if you have overlay FS as part of your kernel, and overlay FS is overlay file system, and then overlay and overlay 2 are the drivers. You could actually go out and do your own mount. You could mount things together. You could do a mount command like you see there, which is essentially kind of what Docker does. It defines a lower directory, an upper directory, a work directory. Those are just, and then just points them to directories on your disk. And at that point, you could actually do the same kinds of things that Docker does. You could create files out there in different layers and see them the same way in there. So you can actually mimic this on the operating system itself. But what happens when we pull an image? Well, when we pull an image down, we get the different layers down, and if we were to do a Docker inspect, we would see the layers represented by the digest identifier, again, that algorithm and the checksum. And if we were to go in and do an inspect and look at JQs, kind of like a formatted grep for JSON stuff here, we can actually, in the Docker inspect though, there is information that says the lower directory is this directory on disk. But notice here the lower directory has a couple of directories chained together. So this particular image has two directories or two layers that make it up. They just combine them together and they call the whole thing the lower directory. Then there's the merged dir and the diff dir. And note that those are actually the same area, that one, the upper level directory, and the work dir. So you can get the core information, like for overlay 2, by doing a Docker inspect. You could go in and find this stuff. So if we were to go in and look then in the Docker, in the overlay 2 directory, the directories look like this. There's a higher level directory with the names. These names would correspond to those things we saw in the last slide, the inspection. There's also an L, a lowercase L directory, which simply has a shortened identifier. It has a very shorter version of the name that we can, it's a symbolic link back. The reason they did that was to avoid hitting page size limits, because they're going to have a bunch of those long directory names start to become problematic. So they just have an identifier that points to that. And you can go out on any system you have Docker on and look at this if it's running the overlay or overlay 2. And if you're looking at layers then, I'm going to just go through these real quick to save time for questions. But basically, the lowest layer, the lower dir, again, a list separated by questions, or by colons, excuse me. If you look in the Docker inspect, you could see that these are the directories that are chained together that form that lower directory. If we were to look at that first directory here, the lowest one, the DB, the bottom one, then we would see that on disk, that has some subdirectories. So layers are this upper level directory, and then within them, they have directories like diff and link. Diff is simply the set of content that goes into that layer. For example, in this case, it looks basically like an operating system, right? It looks like the directory is on there. So this base layer may have had the operating system files on it. So you can actually go out to these diff areas and you can see the content that's in that layer. And then if I were to look at it, I also have in the link, a link that says points back to that, the short name. So on the right-hand side, you'll see the image-based layer, the lower directory, and then the link and directory there. If I go to the next layer, the first one in the list, remember we're going from kind of top down. This is the lower directories. I can look at that as well, do an ls of it. It has a directory, a diff layer, a link, a lower, and a work. In this case, the diff is again what changed for that layer. Think about in that Docker file, some action happened that created this new layer, and that action caused these directories to be on there. It caused some content or some change in there for those directories. If I looked at the link, it would just be a link back to it. And then if I look at the lower thing, guess what? Lower points back to the previous layer. That's how the layers are tied back together, that lower directory. If I go into the next one called UpperDir, this is the UpperDir. If again, I can look at that from the Docker inspect, you could actually see that it has a diff, a link, lower work. Same deal. There's a diff that has a whatever was changed by the Dockerfile command or the command that ran to create that layer. And then if I looked at lower, it would simply point back to the previous lower layer before, and I could look at link, it simply has a link back to it. So you can start to see as we build up this chain with the green arrows on the right, the set of things that we see, and then we just have links back to the other layers below that. Now notice here that in this second one we have this topmost layer here that we used to create this, we had the run area. If we were to look at the history in there, if we were to look at Docker history, you'd see that one of the commands was make directory run systemd out there. That can tell us from one of the commands that was run to make that layer. If we look at the diff area of the second layer, what do we see? In that directory, we see run and systemd. So you can see that the diff in there is where the actual contents of what's in your image, that's where they get put. And then all of those directories get stacked together and linked together, and you get that view, and that is how you get an image that then you can base a container on. So what happens when we create a container? We use Docker run to start the container. And if we're doing this case, run-it just says send it back to my terminal, effectively make it interactive. Once we do that, we get an image ID. And if we look at overlay 2, guess what? There's a new layer out there, this B5065. If we create a new file, let's say we're going to create a new file, so we're inside the container. We've gone inside the container, we just do a simple echo. If we echo and then we look at the diff out there, we look at the directory for the container. Notice that if we look at the diff, we see that file we created. That was the change for that layer. That container layer, but it's that file we just created. If I look at merged, what do I see? I see all the stuff from the previous layers with file 1 on top of it. All the stuff, because remember we had the lowest level, we had the operating system directories, then we had the run and etc and stuff, and then we had file 1. So merged gives you that merged view. And this is just using that standard operating system stuff. That was sort of, I mean, the same kind of ideas behind that mount command that I showed you to tie all that together. So you can see the diff area carries it all together. And the container directory, you can see things in here, the different configurations, JSON files, checkpoints, and so forth in there. Last topic, and then we'll take time for a few minutes for question. Open Container Initiative. So for a long time, Docker was the main kid, you know, on the block as far as doing containers and stuff. There were a few others, but Docker really did it well. Back in June 2015, I think it says here, Docker got together with the Linux Foundation and they started the Open Container Initiative. So the Open Container Initiative basically said, we're going to explain the format that we use for containers. We're going to explain the way we interact with them. and all these kinds of things, give away all the secrets. It's the open source kind of idea there. So the idea is with the Open Container Initiative, if you follow the specification, if you follow the way they do things, then you too can be like Docker. So you can do all the kinds of things that Docker does, and you can mimic that. That's actually led to a number of new tools out there which can work with containers in the same way as Docker does. Podman, Builda, Rocket's been around for a long time. Cryo is more about container runtime out there, Run C. But it's really, Docker doesn't have as much market share anymore, and they did not adapt as quickly as other things did to things like Kubernetes and different things. So really, you'll see it. You're starting to see a lot more of these kinds of other players in the container space out there. Podman and Builda, I think Red Hat 8 is the only one, or did not even include Docker. It just included Podman and Builda. So it's really interesting to see how containers have taken off, and also how much has been built around them. One more quick thing here, put it in plug. Upcoming training for No Fluff Just Stuff talking about containers. Kubernetes is a big part of the container industry or infrastructure, being able to manage lots of containers. Doing a session, workshop on Helm and Customize. Helm and Customize, kind of like package managers, lifecycle managers, too many words on the slide, but basically to help you manage all the things that go into driving Kubernetes and telling it how to run your containers and stuff. If you're interested in that, check back on the No Fluff Just Stuff site there for the list of that. And then there's an advanced Kubernetes, if you're familiar with Kubernetes at all, or if you get a chance to be familiar with it before. This one, they're doing a couple of sessions of that I'm going to be doing. These will be hands-on workshops. We'll have a virtual machine that you can install, run your own system, and you will already have Minikube, Kubernetes, all the things on it that you need to have in there to run it, so you'll be able just to take off and run it and play with it. All right, I've been rambling on for too long, so let's get to some of those the questions.
All right. And actually, before we do, I want to say I'm really glad you brought that up, that you've got those workshops coming, because honestly, that has been, for me, one of the best things that has come out of an otherwise dreary situation that is the pandemic, that I've had the opportunity to sit and learn almost daily from some of the brightest minds in our industry. So if you're familiar with No Fluff Just Stuff, our model's pretty simple. It is attendee-centric, attendee-driven. The focus is on the content, not on the sales pitch, although I do see the irony that I'm making a pitch right now in the middle of some content. But I've been to a lot of conferences. I think I've spoken at around 200, 250, something like that, at least over the last 10 years. And there's really two types, right? There are the types that are big, kind of ultimately vendor parties, and then there are the types that where you really kind of get to dive in. And that's what I've always appreciated about No Fluff Just Stuff, is if you come to one of the conferences, there's no vendor hall. They don't have 2-hour breaks between each session, so you can go and get pitched to in the networking room, which is the pitch fest. Really, we dive deep into the content. Our speakers aren't vendor reps; they're not salespeople. They are hands-on practitioners that not only have the skills to present this information and they're passionate about the topic, but they're also hands-on. They work with this daily in the trenches, and so it's a really great model. But of course, obviously, we're not doing any live conferences right now, but almost every day of the week, every weekday, usually 4 days a week, we do a half day or a full day hands-on workshop like what you have scheduled. And so certainly you can dive into those a la carte. You can find all of them at nofluffjuststuff.com, as well as our upcoming webinars, past webinars, upcoming conferences, and everything else. But you can also opt for the team subscription model, and that's kind of a one fixed price for the entire year. You get almost 200 of these workshops, plus everything that is in the back catalog, everything that's been recorded. And what's nice about that, obviously, you can't go to every single one of these every day, and probably nor do you really want to, but you can share this with your team. And so normally that's a $2,500 value, but we are in the midst of a flash sale. So basically taking 70% off of everything. You can buy that for your team for an insanely good price. And I know with everything kind of being locked down for so long, teams have been kind of wait and see with their training budget. This is a great investment. And not only that, right now you also get a complimentary ticket for the next No Fluff Just Stuff conference. So you get a conference ticket and a year of really high quality learning, live, instructor led, hands on. I mean, videos are great, but I love the idea that at any point in these trainings, I can just ask a question. In fact, I spent all day yesterday getting up to speed with AWS. But anyway, enough of that. Do check that out. nofluffjuststuff.com. A lot of really cool stuff coming up. But a few quick questions. One of the first ones that came up is, Brent, you mentioned how Docker doesn't run really well on Mac OS. Now, a lot of us are thinking, well, we do run Docker on Mac OS because Macs are increasingly becoming the developer workstation of choice. So, can you clarify what you mean and tell us
Yeah.
what won't work or won't work as
No,
well?
it's probably poor wording on my part. What I meant was Docker has to be run in some other mechanism to run on a Mac. I mean, like in a VM or in that environment, you can't just say plop down uh, Docker on there. Sorry, the implementation. That's a better way to say it, I guess. The implementation is not the same on Mac as it is on Linux, because you have a virtual system that you're essentially running it through. The result, the functionality is going to be the same, right? When you're using Docker, you're doing that. But the underlying way that it's implemented, it's not using core Linux technologies and stuff that are natively running on the Mac. It's using a a virtual machine essentially running on the Mac.
So effectively, it's the same, but that's
It's the
the
same functionality that I'm sorry. Yeah, it was probably confusing wording on my part. I didn't mean to imply that it doesn't work or doesn't run there. I simply meant to say that it is implemented a different way. In the same way that you might have, like for Windows, you have a Linux virtual machine if you're using the Linux containers on Windows. Yeah. Or,
That makes sense.
yeah.
Another question that came up is managing patching on Docker images at the enterprise level. I mean, I know how I'm doing this in my organizations, but do you have any thoughts? I mean, basically, I'm doing scanning with something called Aqua, but we're also using a trusted registry and doing and kind of or starting with a trusted registry. We do our own patching as needed and put them into our private Docker image registry, and then build off of those. So every time we do a build, we get the latest of whatever that our images are. But is there a
Yeah,
better way?
I think that's pretty much the same way I'd see it being done too. I mean, you're doing the scanning and patching. If you're getting stuff from a trusted registry, that's a key point.
Yeah.
Being able to get stuff trusted there, and not just pulling stuff off the web here or there or wherever out there. I think that's a key point. We get images from Red Hat or whatever as well. So I think I don't necessarily have a better way to do it.
And honestly, I think one of the best things you can do is sit in on a discussion like or a presentation like what you've just given, and have the kind of skills and confidence to build our own images up rather than going to Docker Hub and getting just some rando stack. That we can get an official image and then build up our stack on top of it that we know every detail of, rather than something that is coming from a Docker registry called absolutely totally not RussianHackers.com.
Yeah, and if you go out on Docker Hub, I mean, a lot of times they'll have the Dockerfile or such associated with the image. I mean, when you download it, you can actually go out there and look around, and sometimes they'll have the Docker file that shows you exactly what they did with it, and you can look and see, there's stars out there of how many times it's been pulled and those things. Now, that's not saying that's a guarantee, but still, you can get some impression of that. And there are other tools. I mean, for security scanning and stuff, there's one called SNYK, SNYK. That's fairly, I guess it's still kind of new. Docker, I think, just announced they integrated it for security scanning in there with the layers and such. So, yeah, I mean, it's like anything else, right? You don't want to just go out and pull down what you found on Google necessarily and run that installed on your machine. But there are some trusted sources, and there are scanning tools and stuff you can use for it.
And let's see. And in fact, there's a question in here. So if you run Docker in production, would you regularly rebuild images and containers and to keep patching up to date? I don't. I'll say for me, and I want to, and I'm saying this first because I kind of want to validate what I'm doing against your expertise. So like I don't, but we do regular scans. So so if a dependency is vulnerable, I get a notification. Oh, we have a vulnerable dependency in production, and likewise if there's an exploit or something wrong with the images that we're using, I get a notification, and that just kind of becomes like a Jira ticket or an issue.
Yeah, same sort of thing. I mean, like a CVE, if get a
Mm-hmm.
CVE out there and a security CVE, you've got a certain amount of time to do it and stuff. But in general, no, I'm not going out and rebuilding my images because I consider that once I've got them there, and they're working for people, there's not, you don't want to mess with them. But if there's a CVE or something comes up, then yeah, we treat it sort of like the same thing. Look and see who has a dependency on it, see what it affects. What do we have to change? Those kinds of things. Yeah.
And a couple other things. I know we're just a few minutes over time, so I want to wrap this up. But a question did come up about how a container can be configured to access and modify files on the host, which aren't part of the layer of the image. And I believe that was answered. And both in your presentation, you talked about mounts, but also Mark very helpfully put a link to a discussion on that as well. And then I'm just looking through. Somebody suggested that Rocket is dead. I'm not familiar with that tool, so I can't speak.
Honestly, I haven't heard anything about them lately, so it may be the case. They were one of the early ones out there too, around Docker. But yeah, I honestly haven't heard much about them, so it could be the case. Yeah.
And then I really think that's about, and that's the only difficult thing about this world that we live in now is that this is all emerging and evolving very, very rapidly. So tools are coming, tools are going. And that's really why I like this format, to kind of get an idea of where are we right now. Because even an article that was written a year ago, just that this time in 2019 could be hopelessly out of date. I mean, this is an exciting space and we're solving some really difficult problems as an industry. So that is awesome. And then their question did come up. What was the scanning tool I mentioned? It is a commercial service. It's a commercial offering, but it's called Aqua. And I linked to that in the chat, aquasec.com. But they've got some great kind of container scanning and some tooling around that.
And there's another one too, like I mentioned, SNYK. I think Docker has actually just integrated that in their latest. I think it may be pronounced Sneak or Snick. I'm not sure which, but SNYK. And I think Docker just integrated that into their own release or an upcoming release. So
SNYK.io. I also linked that in the chat.
Yep.
And I'm just looking here if there's anything else. No, I think that really is it. You covered everything. That was insanely comprehensive. And I really appreciate this because technologies like Docker, like Git, for most of my in most of my daily life, I kind of get the basics. And I know I know a handful of commands. I've memorized a handful of commands and work with it, but being able to sit down and understand what's happening in that mysterious .git folder has made me so much more powerful as a developer.
Absolutely.
And understanding beyond, I've got this nice little movable runtime environment, and getting in some of the details, again, that makes me more powerful as a developer, as an architect. So I really appreciate this. And lots of big thanks in the chat. One more mention, somebody uses something called Twistlock for image scanning.
Oh, yeah, Twistlock, yep.
And
we use Twistlock as well, yeah. I haven't used it personally, but I know of it, yeah.
Awesome. Well,
yeah,
Brent,
fantastic.
Again,
thank you, everybody.
I want to thank you for your time and for your expertise. And for everybody, I know people are starting to trickle off because we have gone over time, but for the substantial number of folks who are still here, thank you. And as always, look forward to seeing you at an event soon, whether it's virtual in this sort of format or in the unforeseeable future when we can do these things live again. So everybody,
absolutely,
thank you so much. Have a great weekend. Stay healthy and stay safe.
Thanks, everybody.